Okay, so hi everyone. Thanks for making our time to attend this talk. Today I'm going to talk about a project that I'm kind of really excited about, and it kind of lies in the domain of using large language models. And I know Alan sort of spoke about how these models are super effective in building like really interesting like HCR interfaces. And so my talk is just a level down the stack today, looking at a specific problem, how we can use LLMs to generate visualizations, and then think through all the problems that sort of come up with we trying to accomplish this task. In terms of background, I'm an ML GDE, and I joined the program about 5 years ago, and it's been such a pleasure to be part of this really, really exciting community. Lots of really interesting people, lots of really interesting technology ideas. And I recall that like 5 years ago, I started out with contributing to just training TensorFlow models and specialized data, contributing to TensorFlow.js, contributing pre-trained models to that repository. And over time, it's been just really, really interesting, sort of contributing to the TensorFlow community and also conducting ML research. In addition to that, I'm also a research scientist at MSR. And so my background is human-computer interaction. And I spend a lot of time now looking at scenarios where we pair a human with an ML model to solve a task. So for today, I have 4 high-level areas I'd like to talk about. And so first of all, a motivation. Why might we be interested in using LLMs to automate the creation of visualization? I'd love to get into a demo, assuming all goes well and the demo gods are kind to us today. And then next, I'll look at the system components. What are different system components that we sort of string together to make such an application possible? And then I'll look at how we could think of ways to evaluate systems like this. It's kind of really important that we have some sort of evaluation metric or evaluation suite, such that as we make changes to the system, be it prompts, code scaffolds, error correction, we just want to make sure that all of this improves the metrics and we don't have degradations. And then finally, I'll conclude with conclusions, lessons, and next steps. So one thing I wanted to mention is that all of this work is public domain. Code for this project is available on GitHub under MIT license. So I definitely will encourage you to sort of look through the project and sort of get started. And I'll put a link in the description at the end of the talk. Okay, so in terms of motivation, why might we be interested in automated visualizations? And so I'm sure that many of you have had this experience where you might have a spreadsheet with hundreds of thousands of data points, and then it doesn't really inspire thoughts and insights. But then if you see these charts where you see like, let's say, histogram or bar charts, you can start to make good decisions of, it looks like our sales was really high in March. Like what was driving that? How can we replicate that sort of spike in sales across the rest of the year? And so the core idea is that visualizations reduce the cognitive load associated with sort of extracting insights from large data sets. However, the challenge is that most users just don't have the skill or just don't have enough time to put in the effort to create these visualizations. And so the idea is that in order to come up with good visualizations, first you need to get familiar with the data. You need to ask the right questions. And once you've done that, you need to come up with the right encodings or transformations. Do I use a bar chart? Do I use a pie chart? Do I aggregate my data? Do I create new columns from existing columns? And so there are a lot of decisions that you need to make. And then finally, when you figure out all of these, the final thing is to sort of implement the visualization. And so in this case, you might use a GUI like Excel or Power BI, or you might just write code with Matplotlib. And either route requires a bit of skill, and a lot of users don't have the skill. And so from this perspective, there's been a ton of research and ways to sort of recommend visualizations to users. And the net goal of this is that for users who don't have the skill, then all of these abilities become available to them. And then for users who already have that skill, maybe we can sort of cut down the amount of time they need to create visualizations. And so the core value proposition is, how do we empower users in the creation of visualizations? How do we make visualization authoring a better experience? And so ideally, with LLMs, we can simplify this by making the core interface to all of this process text. And so imagine that the user could just point a tool or a system at the data, and then proactively the system could come up with a few interesting things. Let's say explore the data, come up with good hypotheses or questions, and for each of those questions, offer visualizations. Or we could offer a natural language interface where they could say things like, I'm interested in these, can you help me create visualizations that like sort of address this question or this goal? Okay. And so right now I would like to um, switch a bit to a demo. And I'll talk a little bit about how you might want to spin up this demo in the future. So screen share. Okay, so the interface you see on the screen, and Madisha, if you can give me a thumbs up just to verify that like the screen share sort of is going through correctly, I think that would be great. So assuming all goes well, the screen share that you see is the interface for a tool called LIDA. So LIDA is like a tool that implements some ideas for generating grammar-agnostic visualizations using LLMs. The idea here is grammar-agnostic means that LIDA makes a core fundamental decision of representing visualizations as code. And so as long as we can represent visualizations as code, it means that like we can use any programming language, R, Python, and we can use any visualization grammar, so Matplotlib, Seaborn, Altair, as long as those grammars, those visualization grammars can be represented as code, we can then use a pipeline like this to sort of generate visualizations. And so going forward on the interface, you could either select a data set or we could use one of the existing links that are available. In this case, we'll look at the SP500 data set. Okay. And I thought I had this cached earlier, but looks like if we're doing a full brand new call. So let me see if I could. Okay. Let's see. Of course, demos always have like a bit of this effect. Let's just take a look, ensure our server is running, and do a couple of back checks. And so while this is spinning up, I'll sort of talk through the pipeline. And so LIDA sort of structures visualization generation as four main sections. In the first section, once we provide our data, we have a summarization module. And the goal of this module is to ingest your data and come up with a natural language representation of the data that the model can use for every subsequent task. So there are a couple of things to keep in mind here. The first is that our data might have arbitrary size, tens of thousands of rows, millions of rows. And so from that perspective, we want a representation that is compact, is natural language, but at the same time, it respects the limited token budget for LLMs. Let's just do a quick refresh here. Select our model, GPT Turbo. And so one other thing I'd like to point out with LIDA is that it supports multiple LLMs. In this case, we could use OpenAI LLMs, models from Google, Palm, Cohere, Hugging Face, and it's sort of designed such that the LLMs underneath are switchable. And so, yes, we got things running now. And so in this case, once we selected our data set, it gets passed to the data summarization module. And summarization is done as a two-stage process. In the first stage process, we take all we know about visualizations and we come up with heuristics for the data. So in this case, we might try to use a tool like Pandas to sort of extract the atomic type for that field. And so in this way, we've sort of discovered that the atomic type is date. We can compute the mean and the max for that field if it's a numeric field. We can construct a list of non-null samples from the field. We can compute the number of unique values. And then once we have this Bayes representation for each column in the Bayes set, we can then give that to an LLM to sort of annotate or embellish or enrich that representation. And in this case, we ask the LLM to predict the semantic type of each column. In this case, it's a numeric field, but it's also date. And also we ask it to come up with a description. And so in this case, it says the date of the stock price. And the core idea here is that if we have this rich representation of our data, then we can then pass that down to subsequent modules. And so in the next module, we have the goal exploration module. And the core task here is to come up with potential visualizations that make sense given this data representation. In this case, we structure it as a multitask prediction problem where we ask the model to predict a hypothesis, a question. We ask it to come up with a visualization title, and we also ask it to come up with a rationale for why this visualization might make sense. So you might have heard of chain of thought prompting, such that where we sort of structure problems such that we ask the LLM to sort of provide like justification for its work, sort of think step by step. And once we do that, we get much more semantic or correct responses from an LLM. And so here the model has come up with about 5 different like ideas. And so automatically it takes the first idea, what is the distribution of stock prices? And then what it does is that it generates code that addresses that goal given the data summary. We compile that goal, we do some error correction, some pre-processing, post-processing, error recovery, and then we present a visualization to the user. And we can do that for all of the different goals that the system has come up with. And in the case that any of these goals just don't meet the user's requirements, the user can always come in and type, sort of describe their intent, and then click generate, and the system will about do the same thing. Next, for each generated visualization, we can then dig in and do things like, let's say, convert this to a bar chart. And so ideally, the goal is that the system takes the representation of the visualization, the code we have here, it takes the additional instruction, and then we go through the same process. We generate new code, we compile it, and then we show that to the user. So previously it was a line chart, and then now we have a bar chart. Of course, we can see that there are some mistakes here. The system is not perfect, and so we can see that the x-axis is sort of cluttered. And so maybe we might ask the system, the x-axis is cluttered. Can you go back and sort of fix this, make this more legible? And the system will actually do that. Another thing that comes up when you put a tool like this in front of users, and so the user might have the curiosity and interest to sort of come up with good things to ask the model to do. But however, they might struggle sometimes to sort of judge the correctness of the code or the visualization that has been created by the user. And so from that perspective, you could use the system has an explain feature where we could ask the model to sort of walk through the code that it has generated and sort of post hoc or retroactively sort of explain what it has done. And so in this case, the system starts out with an accessibility description of the field, says this is a bar chart created with Seaborn, and talks about the size, talks about the axis, and just the physical appearance of the chart. And this can be super useful for accessibility of building accessible systems. Next, it talks about the sort of transformation that was applied to the data. It says here that we've converted the date column to a date type using the pandas to date function, and that errors are handled in a specific way and null values are dropped. Next, it also describes how, and for each of these descriptions, it sort of pairs the code that's associated with that. And typically in some use cases, I've seen situations where the user sort of reads through the description of what the code does, and then might go back and retroactively sort of modify the request or the make changes to the charts to sort of address those goals, those mistakes. And so another thing that you could do with a system like this is that let's say we go back and we say like convert this to a bar chart. We could also get the system to sort of self-evaluate itself. And so in this case, we could run this as a self-correction or error correction module in the background where the system could retroactively look at the code that it has written and sort of evaluate it across multiple dimensions. In this case, we select the dimensions that are used to evaluate the code that was generated. And this is all from research on like visualization generation. But let's take a look. So on the first dimension, it says there are no bugs or logic errors. It says that no additional data transformation is needed. Compliance here has to do with how well the generated chart meets the goal that was specified by the user. And so it says that the code here meets the specified visualization goal. However, on the type dimension, it sort of rates the visualization of 4 out of 5. And it says that the bar plot is an appropriate visualization here. However, a line plot might be more effective. And so you see these sort of suggestions. Let's say you use the pie chart. The system might say, okay, a pie chart is better just because it allows just better visual comparison of quantities. And so it turns out that like large language models like GPT 3.5 and above, they're quite good. They have very broad world knowledge, and they're able to sort of encode visualization best practices. And the goal here is to sort of figure out the prompt structure that helps us apply all of that knowledge in just creating good visualizations. Now we can click a button that says like auto repair, and then sort of repair that chart. And so here it just reverts back to a line chart. And then finally, we can take the same approach, given some code. You can ask the model to come up with potential recommendations of visualizations that make sense. And so based on this, we just ask the LLM, what are other visualizations that might make sense given this that the user might be interested in, and the system will go ahead and sort of come up with potential visualizations. In this last example, it shows like a kernel distribution of stock prices over time. Okay, and so this is just a very fast, high-level walkthrough of a demo, a concrete realization of how we might take LLMs and pair them and sort of integrate them in the process of generating visualizations. I sort of skip over the infographics part. That is still much work in progress, but I'll sort of get back to that during the rest of the talk. One final thing is that we could select different visualization grammars. And so in this case, we just have 4 here. In theory, we could select visualization grammars from other programming languages and sort of integrate that into a common workflow. Okay, and now I'll get back to the slides. So in terms of system components, I mentioned earlier that there are 4 high-level components that sort of make the system work. The first is summarizer. So the summarizer ingests the raw data and sort of has this 2-stage process where we use our understanding of just data analysis and visualization generation and come up with like a representation of the data set. So compute things like min, max, number of unique values. And then we can take that representation and give that to an LLM to sort of enrich it with more semantic fields like semantic types and description of each field and the entire data set. Now, once we have that, we can have that as some sort of grounding context for every other activity that we ask the system to do. So for example, when we ask the system to come up with goals, essentially what we're doing is that we're asking the LLM to take the position of a data analyst, sort of come up with potential visualization goals that make sense for the data. And so the LLM is able to do this because it can ground all of its explorations or its generations on this summary that we have generated for the data. Next, we can have this module that generates, explains, evaluates, and repairs code. And essentially, that's what sort of powers the visualization generation. And then finally, there's an infographic module that's optional. And what that just does is that it uses a latent diffusion model and does just image to image generation, but conditioned on some style text, some style prompts. And so here we have a bar chart, and we sort of condition it on skyscraper text, and we just do image to image generation with a low strength parameter. Of course, you want to use a low strength parameter just to make sure that the output sort of maintains the structure of the input data set, but at the same time yields more interesting and more aesthetically pleasing infographics. And so that is the core of each of the different modules. And so I will share a link to the repository for this project. And I think the most interesting thing there would be to look at some of the prompts that are used to sort of construct to construct the prompts for each of these modules. And so the summarizer creates a natural language summary of the data. And so here's an example of what the prompt might look like. You're an experienced data analyst that can annotate data sets, always generate the name of the data set, generate a field description. And here's what the output looks like. Next, there's a goal explorer. And so here's what the prompt might look like. You're an experienced data analyst and a visualization specialist. And more importantly, we sort of make some requirements on the structure of what it can output. So I mentioned earlier that for each goal that the system generates, it has to come up with a question, a hypothesis, a visualization title, and also a rationale for why that visualization makes sense. And then finally, the Viz generator module takes in a goal, takes in a summary, and also it uses a code scaffold. And so, for example, an important distinction here is that we don't just ask the LLM to generate visualization code. Instead, we provided a code scaffold where we have like a plot method, and it's rather than generating just code freeform, we ask the model to sort of fill in the parts of the scaffold. So this becomes very, very important to ensure reliability. And then the infographic module is optional, but the idea is that like we take valid visualizations, we pass it through a latent diffusion model, and then we get stylized versions of those base visualizations without compromising much of the structure. And so I'll skip a little bit of related work and I'll go into evaluation. And so naturally, there are a few issues that come up with evaluation. The first is that LLMs are stochastic and bugs might occur, especially when we're trying to generate code that compiles. And so we need some sort of measure of reliability. Next is we might be able to generate code that compiles. However, how do we sort of continuously measure visualization quality? And then finally, there's always a challenge of memorization. So how much of the output is based on what the model has seen during training, as opposed to it being able to sort of extract parameters of the task at hand. And so to sort of measure reliability, sort of propose visualization error rates. And so in this case, we have over 2,000 visualizations generated based on about 50 data sets from the Vega data set. And so for each data set, we asked the model to come up with 5 visualization goals. For each visualization goal, we asked the model to generate visualizations across 2 grammars. And then overall, we sort of measure like what percentage of times do we get like visualizations that just contain like compile errors. And then and so the charts we have here is just a small ablation study that sort of shows that like when we include just the schema as a summary, and so just a list of the tables in the data set, we get about a 10% error rate. However, when we actually include all the details we have in the summary, and so we include like just the properties of each field, and in some cases we sort of enrich that representation using semantic types, we get much lower visualization error rates, and so down to about 3.5%. Next, I also showed the ability of a model to self-evaluate code across multiple dimensions. And so we can use a much larger model like GPT-4 to sort of compute the scores, and so as a way to sort of evaluate the performance of smaller models. Okay, so in conclusion, there are 4 high-level lessons I think are sort of useful here. The first is, of course, I think, and I know that Alan sort of hinted at some of these. If you ever have a problem where you know the structure of the solution, as opposed, and that represents your domain expertise, as opposed to having the model sort of solve all the problems, is a great idea to sort of separate the parts of the problem that you sort of understand and bake that into the generation process. In this case, we rather than letting the model generate the entire code for the visualization, we sort of use like templates for each of the different languages we're interested in supporting, visualization grammars we're interested in supporting. Another way to do that is to also do things like 2-stage summary generation. So we take all we know about like generating representations of data, and then we can then give the LLM to enrich that base representation. And then finally, structure the problem such that we minimize latency. So every single step is a single call to the LLM. Then finally, design evaluation benchmarks has been critical just to sort of tune the scaffold, tune the prompting system, and sort of ensure that the overall system is getting better. So some future work, there's still a lot of work to be done. There's a lot of opportunities to improve the reliability of the system. There are still cases where the system might not just come up with visualizations that are valid. There are differences in behavior across models, and so the best performance you get from really large models like GPT 3.5 and 4, and with smaller open source models like 7 billion and 13 billion parameters, the error rates are still very, very high. So this is like an open research direction. And so from that perspective, it makes sense to look forward to sort of explore ways of sort of tuning or fine-tuning smaller models such that they can approximate the behavior of larger models for these sort of capabilities. So at this point, I'd like to stop and sort of take questions if that works. And while I'm waiting for questions, of course, there are limitations to this approach. The first is the more representation the visualization grammar has, the better the performance of the overall system. And then also, this entire application or system requires code execution, and it's important that all of this runs in a sandbox environment. So, Noble, did you have a question?
Oh, yeah. Hi. I asked it earlier. But great presentation, first of all. I'd love for you to share any trade-offs, challenges you had to make. For example, having the model sort of self-evaluate, that seems like a challenging proposition.
Yeah, so ideally, you want a human evaluating the subjective quality of the visualization. And so that typically is the gold standard. But in most cases, you just didn't have that as skill. And the next best thing you have is to have a really, really capable model like GPT-4 sort of take on the persona of an expert and sort of evaluate models across multiple dimensions. Of course, clearly, the performance of GPT-4 on that task of self-evaluation is significantly better than even GPT 3.5. And then when you start getting down to the Llama style models, you just can't use Llama style models for this sort of self-evaluation. They just don't work. And so it's a trade-off. In the absence of gold standard human subjective evaluations, the next best thing is GPT-4. And the other reason why these sort of signals are good is because they can be a good way to sort of approximate human behavior when you want to, let's say, fine-tune smaller models. So let's assume that you had like a 13 billion parameter model and you wanted to sort of fine-tune it towards just better capabilities across all of these dimensions. And so the next best thing to do would be to sort of distill GPT-4 behavior, its evaluations across these dimensions. And so you can use that as a filter on the kind of data, data that's used to fine-tune these small models. And this is an ongoing sort of area of research. So, great question, though.
Thank you.